good make your segment? It's like a rough, very rough. Very rough. I think it's too early. I think it's like you have to go through it. Because you still don't have a sponsor, you still don't have a heat. So that's why it's yeah.
How's it going? Oh, yeah, it is time to start, right? Just everything's going so smooth. Cool, welcome back. Tomorrow's the big day of submitting homework number 1. So one thing that a few people have asked about, and so I thought I would go over before we jump into anything else, was just like how to get a submittable thing. And my process, so the main thing is like, because we're working in Blackboard on Husky CT, PDFs are our main like back and forth submission. So click on File and then create a print preview. Don't click that download as button, because that usually results in like a LaTeX 500 error. So just create a print preview, and then from there it gives you a nice like static website of whatever the current state of your code is. So it's not going to run all the cells, it's not going to check to look for errors and anything, it's just whatever's there is there. And then from there you can hit Control P or Apple P on Mac, but some kind of command print, and then save that page like as a PDF. That's the main way to like get that PDF to Husky CT. Cool. I would love to have like better solutions that incorporate all of the hard work, but this is at least like something something workable. Yeah, so File and then Print Preview is the main thing for submission. Is anybody working on something more interesting than exporting PDFs? Like errors that came up? Yeah.
So I had a question. So that doesn't show like what outputs?
It does show input output. So here, let's get rid of the file. Oh my god. So like here, if I'm gonna calculate my volume, 12.5 times, I should know it by now. Print box volume is so right now I have like 2 things printed out. I'm going to change the formatting though. 1.0F, and then let's do 1.3F. And when I make a print preview, it's just going to take whatever the current state of that notebook is and turn it into just a static web page. So right now, that was the 46th input that I had, and it's telling me that is the case. So sometimes that, like if you delete code but it still happens to work, there might be like missing variables, but but it is showing like whatever it happens to be. Yep.
So should we do like a run all before we print to it?
If you want to double check that, like that's a great like reproducible step of will this code work if I give it to somebody else. But if it's working and it's kind of and you don't see any issues with it, then it's okay to leave it like in this format. Like I'm not expecting this to be a 1 then a 2. It can be run out of order. That's okay. I get it. Yeah, let's double check something. If we start that still works. If you start getting really long lines of code like this, you might end up with a case where oh, this one does. Okay, nice. So sometimes print preview does a nice job of like bringing it down onto the next line, and that's what this one is doing. That even though I made my code line really long and I had to scroll back and forth, this one brings it down onto the next line. So that's okay. So we can just make a print preview and everything's good. If you try to just print that, like if I try to print this directly, then that's where we can see my code got it gets cut off. So all the hard work that I just put into my fancy formatting, some of that gets cut off on a really long line of code. If you want to follow NASA's code structure, nothing can ever be more than 80 characters wide. So if it's more than 80 characters, put it on a new line. Just make it something new. We don't have to do that though. We're not working for NASA. Not yet. Not yet. Did anybody like reach convergence, the AI convergence with their computer the other night? And now the computer knows more about you than you know about yourself. No issues like that. Turn off, like slam the phone against the floor, save yourself. All right, I'll check in, see where people are at and what might help. Oh, all right, cool. Above empty, right? Yeah. Yeah. Is there still? Is everyone?
I'm on guest this week.
Okay, guess. Okay. Yeah.
No, I design project schedule. You know, so that so like or like he gets like calls upstairs like, hey, and I was like, submitted already? Okay, I'll let it.
I'm trying.
No, I tried to submit like I thought it was already going there.
And you just know.
No. And then even though I was trying to submit it there, like I had to email it, it didn't know.
So where were you trying to spend that one? Where were you trying to spend that one? Where do you live?
Gary.
Okay.
No, it's just like one of the debates. Not hold on.
Unfortunately, don't notice that. Just I guess I think out there it's going to give you. They do have a guest. And so whenever you might walk in a lot, you know, your email, get a guest code, and use it. Yeah. So I think at least the way that I thought of it. She brought the note on the website there. I might want to know. Yeah. Don't know what it is. We've never used it, but. That's my two. Yeah, I was like, sorry. All right. To be fair, in their defense, we talked about it Monday, and he was like, "This is due tomorrow." He also said it should take like 30 minutes. It's all really long that. Just move myself on.
Yeah, we have to meet up to.
Yeah.
We have to meet up to do the schedule.
It's a very rough. It took me like 45 minutes.
Yeah, but what
It took my team like
what if you like wanted what's the word? What if nobody was available?
Back space time, have one partner make it up for everyone else.
Yeah.
Just start guessing. They're really good. It's really good. I did 70% of it myself, and then just on the last 20 minutes.
But also, you also make it like an assignment on the CCP. So if you just want to do like your activities for your it will not pop up.
Some of it's so just that one.
No, I know, but you know how like
it doesn't show due yet.
Yeah. So no, it doesn't come up on the like your assignment.
It just doesn't show due date.
I feel like I forgot. What's that? Like activity?
Yeah, exactly. One people die on it.
I won't know what I'm getting until it's halfway, because I think I'll have
Like Randy, like 10,000 miles.
like 2 summers in EV, savings investing, and no debt on a college next year. It's a no debt. I would say both. That's already pretty good. Oh, it is. I'm saving more now. Multiple summers. It's like 0 to 5. So many people are like, and maybe want to change. For 60? Okay, 996. Well, it's just much older than I'm talking year round data, 63 double.
Yeah, he wants like 2020.
2024. 2021. Year round data. Rating 450. Yeah. Heavily revised. Like, I genuinely believe they should fit 50%? Yeah. No, I swear to God, it's not. Or the phone said it's wrong. No, because like it's the actual phone ranging from 78K, real quick. 78K. Yeah, I was doing the previous letter. Now things are coming in. It's also got 21,000 miles on it. He doesn't get 20,000.
Yeah, that's what I don't know. Yeah, I'm not. Yeah.
Yeah, and sometimes people have exactly this. So like it's like someone else. Yeah. Yeah. They ran this without time, and then they bring it down. So they part of their workspace, their namespace. Yeah, there's like three things going on. One is trying to look at just plotting the population here. That's the first part. And then the next part, we make an assumption. Yes, predict population with a different population. From there, just integrate this equation. This is the exact function. Or not do calculus at all. Okay. We're going to, so that would be, you can also sort of prove it now. Okay. Yeah. So that one would be like the heat. Because DP, it says use methods make heat. Then the solution to that is P equals heat. Oh yeah, maybe we can make that. There's some constant the module. Oh yeah. But that's the three things that we boiler, actual world population, heat. The recording and yeah. Probably because your previous population is always zero. At least if it's a flat line and it's supposed to be exponential, when the solution is that you started at zero and it's never at zero. So usually it's exactly. Yeah, so once you have like initial population, it should grow. It should. There might be other issues. Okay, because
I mean, what is that? Gen 3 CPFP using the 1 for a while. Is
Yeah, yeah, that works.
It's debatable now.
Yeah, so now you have population
So,
but there's also an integration constant, like P equals, yeah, you can do plus, but really it's like, because we're dealing with log scale, P is constant, yeah, yeah, exactly. That would be like the earliest population we have. The earliest it helps to kind of shift over by 90. So T minus 90. P0 is. And I can show them because I think here it's that's a problem.
no. Okay, so 550. These are all. What is the specific?
So right now you're just creating the one value of the comp at a time. Yeah. Even the same return, because you're dealing with rays, you can put rays into like natural just the same.
But it's not two, which is they want it to be bigger. To be fair, I don't think these are I think you that's not torque curve.
Just say more about it.
Cool. So we're looking at kind of like world population kind of problems all the way down here. So we've got like three different things that we want to compare in this process. And this is a general kind of like numeric. If you're doing, especially like senior design right now, you're gonna create some kind of model. It's gonna be awesome. It's gonna solve all these problems. It still needs to go through 3 steps: demonstrate convergence, verify that the result is what it is, like use some kind of function that you know is right to compare to your either finite element or CFD or something like multi-body dynamics, so that you can verify that your code and the actual value are the same. Then the last step is even better, is like validate, like take an actual experimental measurement, and that's what we have. We have some real measurements of world population, and we're going to make the assumption that we can approximate world population with exponential growth. Like dp dt is always k times p. So if this is our like differential equation, then the solution is that p at any point in time is some p0 times e to the kt. But I don't have population at time equals 0, so to make my life easier, I'm gonna shift everything by 1900 years. That way, p of 1900 is p at 1900 e to the k times 0. And just, again, just so I can use like the actual values that I have. So this is like my analytical equation. And there. I'm gonna be fancy today. Start putting in some labels. And I want to give it an actual trying to be fancy. So measured populations, those are these squares. And roughly, if I squint, it looks like exponential growth. The bigger the population, the more it changed. So I think I'm on the right track. So now let's create, let's say T is going to go from linspace 0 to, it's going to start at 1900, go to 2020. And my analytical result, since I have an array of time, this independent variable time, I can plug it right into an equation and say pop 0 times the exponent of kg times t, and I should define kg, right? Yeah, down here. And then I should also actually plot it, right? T, P, A, N. I'll do this one as like a solid line and put a label. And this is usually what I see. And not usually, but I see this a lot. Like I plugged in the initial population, but it looks different. But this is assuming that population 1900 was actually population at year 0. So again, I want to shift everything by 1900 years. And now I've got like this solution that, again, if you squint, they're pretty close. Not bad. What about for Euler? So the 0th order like integration is just whatever the population in 1900 was, that's going to be the same, like as if nothing ever changes. But we'll do one better approximation than that and add dp dt in the year 1900 times delta t. So p at 1900 plus k times p of 1900 times that delta t. And I'm going to do the same thing, like 1940 is p 1920 plus k times p 1920 times delta t. So that 20 years again. So rather than writing out one at a time, I can put this inside of a for loop. So P Euler is, and well, let's define our time first. T numerical is a range, not a range, 1900 to 2021, steps of 20. I'll initialize my Euler to the same length as Tn, my numerical time. And then I need that initial value. I don't want to solve for initial population. I want to plug in an initial value. So that first value of Euler, that is pop 0. And then start at 1, go to length of t. So population Euler of I is going to be P Euler I minus 1 plus kg times P Euler bracket I minus 1 times dt. And I can't spell. And oh, yep, because this should be t sub n. I don't want to loop through t values. I want to use the same time that I defined for my Euler integration. Now I've got half or quarter of the McDonald's arch, some of the red and yellow. And talking about like convergence and like verifying that this process is working, like right now there's definitely a difference between this red and yellow line. What would get them to be closer to each other? What do I need to change? Do I change like the function itself, the for loop? How do I get it closer to each other? I want the red line and the yellow line to be like right on top of each other. Did anybody get that to happen? Yeah. You could change k. So we could say that this kg is actually like 1.5. There, I overdid it, but you could keep varying kg until it gets to the result that you want. But then that's not really showing that these two things are the same, right? Because that would mean that there's different growth rates depending on Euler integration versus like exact analytical integration. But yeah, that would work. That's one way. What's another way that like red line and yellow line are the same? Is the red line going to change? Like for a given k and a given initial population, is this ever going to change? Can I get a different solution for that dp dt equals kp? It can't. Like once you have like that, once you say this is the solution, whether it's like a sine wave or an e to the negative ht, like it's just that is it, that you're done. But what we're looking at with numerical methods is like convergence, that we made an approximation that the slope from here to here is constant. But if we make that smaller, now the slope from like here to there would be constant. And if we make it even smaller, then the slope is only constant for smaller and smaller intervals. So if I take this and change it to 10, like my time step, then I get more dots because I calculated more things, and they're getting closer to that red line. If I make it even like super small, now I get a population every year, and the growth was only constant for 1 year at a time. So slope, and it gets closer and closer to that red line like that. So I demonstrated that my numerical results, as I increase like the number of calculations that I do, converges to my verified. Now I've like verified the result. And then if I want to report like how accurate this thing is, like can I validate this assumption? I could say like what is the error between 2020 population and my prediction? And that would be like my validation step. So that's kind of the 3-step numerical process. All right, cool. So we got some of that going. And then there was a question. Yeah, we still got some time. Question about doing like how do I figure out how long these things take to run? Like, so with this exp Taylor function, this kind of long function, it's manually creating truncation error in that e to the x function. So if I just ask for n of 0, then it's just going to give me 1, no matter what x is, because it's just creating a 0th order polynomial, which is always equal to 1. And then I can keep adding terms to that, and it should get more and more accurate. But at some point, we're going to hit a limit because our computer can only store numbers so well. So like 1 over 100,000 factorial is basically 0 to a computer. There's no difference. And there's an extra like time cost to it. So let's figure out what that time cost might actually be. I only want to time like just, again, like time it is always just minimal things, just little things that we want to figure out how long they take. So we'll try 1 and 2. One and 10. So when I went from a 2nd order polynomial to a 10th order polynomial, I did 5 times as many calculations. Like I had to go through the loop 5 times as many times. And I went from around 1 microsecond, like 0.8 microseconds, to around 4 microseconds, 3.9, about 4. So 1 to 4 is roughly a factor of 4 for 5 times as many calculations. I'm going to make a prediction that if I multiply by 5 again, it's going to be 4 times 4, like 16 microseconds, something like that. And what do I get? Instead of 16, I get like 38 microseconds. On a log scale, that's pretty close. And really we're talking about like log amount of time. Like, is this thing gonna take nanoseconds or microseconds or full like milliseconds or seconds? Like if calculations are taking seconds to run for something like EXP, it's like just forget about it. Like don't run that thing because it'll take too long. Like someone's trying to log into the internet and it's trying to calculate EXP of their sign in or something. And from here, if I'm trying to extrapolate these results even further, we could even use that like lin, like we went through the work of creating that lin interp function. We could use that as like an extrapolation kind of thing, right? Lin interp, I could say 100, 1, 2, 3. My first data point could be 10 and 3.88 microseconds. And my second data point would be like 50 and 37.6 microseconds. And now I get that 100,000 shouldn't take around 84 seconds, something like that. So around a minute for, and again, like 1 over 100,000 factorial is 0. A computer, it is 0 for a computer. So really no benefit of like doing that, waiting 90 seconds for this thing to run. Or 90 milliseconds. We're still in the microsecond region, right? 90 milliseconds, 0.09 seconds. But still, it's too long. Like, who wants to wait that long? Makes sense for like using the timer, trying to figure out how long things take. Were there other things that were coming up as you're working, or were there questions along the way? No? The next part, looking at convergence, made sense? Or no? Made sense? A little thumbs up, thumbs down. If it doesn't make sense, halfway. Is it done? Yes or no? Some done, some not done, some done, some not done. All right, not done. We can take a look at it. If it's not done, we might as well take a look, right? All right, so we want to, for the next part, we want to change n. Really, it doesn't matter what x is. We're just looking at like truncation error. I said e to the 1. You could do e to the 20 if you want, but there's going to be the same kind of convergence rate that the more terms you add, the more you converge to whatever that e to the x is. So I want to change n, start at 0, go all the way to, let's say, like 30. My error, I'll just say that it's a whole bunch of zeros that matches the length of n. Go from 0 to length of n, so as many values of n as I have. I'm going to create an error for that. And I'll compare NumPy's EXP versus my own like EXP Taylor. So where I'm artificially truncating that series. Where am I doing that? Oh, whoops, that's why. N bracket I, there we go. N has to be a single value, but I created an array of n's, so I just want to grab one value of n at a time. That's where that error is coming from. And then I should also save these values, right? Yeah. Put them into individual spots inside of that error. And now I get like negative values, but I don't really care if it's negative or positive. If it's different, I just want to know what is the difference. And it looks like by the time I hit 5, there's no difference between the two methods. But let's put that onto a log scale to look at like actual convergence rates. Like a convergence of something usually happens on log scales, like 10 times more accurate, 100 times more accurate, something like that. So I can't see that on a linear scale. So I'll do two things. One, turn this into absolute value. And then two, I want semi-log y. So my x-axis is still linear, but y-axis is factors of 10. And now I'm seeing that it takes really like 15 orders to be almost as accurate as NumPy, and anything above like 1920, there's no difference. Like the computer can't calculate a difference between those two. So here, truncation error, and then at this point we're just at round off error. We just have two functions that are rounding to two different numbers. Cool, thanks a lot.
So you guys